We are working on Engage New York Lesson 12, continuing our discussion of completing the square. By the end of today's lesson, students should be able to rewrite quadratic expressions given in standard form, ax squared plus bx plus c, with an a value that does not equal 1, as equivalent expressions in completed square form. Notice that we're naming the second term in our binomial h and the constant in our completed square form k. I have 5 steps that will help us review completing the square. In the types of expressions we had yesterday, we simply needed to complete the square for quadratic expressions with an a value of 1. Here's an example. Z squared minus 5z plus 8. Our first step is to focus on the a and b terms. What perfect square will factor to this a and b term? I rewrote the expression on the right in pink for the a and b term, and you can see that the binomial squared that will get us z squared minus 5z is z minus 5 over 2. Because when I multiply z times z, I will end up with z squared, and when I multiply negative 5 over 2 times z and negative 5 over 2 times z again, then combine my like terms, I'll end up back at negative 5z. If you need to pause and check this work to prove that negative 5 over 2z plus negative 5 over 2z equals negative 5, I suggest doing that now. Step 2 asks us to expand our perfect square. Again, I'm following these steps on the left. If I expand my perfect square, I end up with z squared minus 5z plus 25 over 4. I get 25 over 4 because negative 5 over 2 times negative 5 over 2, numerator times numerator, denominator times denominator, is 25 over 4. Step 3 reminds us that if our c term in our perfect square, remember this is our perfect square, is a fraction, we need to convert the c term in our original expression, that's up here in the example, to include a common denominator. So my original expression had a c term of 8. I need to convert that 8 to an improper fraction over 4, so I'll multiply 8 times 4 over 4 to get 32 over 4. So notice that I now have my perfect square, right here, PS for perfect square, and my original expression. I'll put O for original. Perfect square, original. Step 4 asks us to adjust our original expression to include the c term from your perfect square. So we can change 32 over 4 into 2 separate improper fractions to include the c term from our perfect square, that's 25 over 4, in our expression. I'll simply split up 32 over 4 into 25 over 4 plus 7 over 4. So to repeat myself, I decided to split up 32 over 4 into 25 over 4 and 7 over 4 so that the c term from my perfect square appears in my original expression. This expression, and this expression are all equivalent. The only difference is how I've written the c term. Here it was simply an 8. Here it was 32 over 4. Remember, that's equal to 8. And here it was 25 over 4 plus 7 over 4, which is equal to 32 over 4, which is equal to 8. So now I have my perfect square in standard form as a part of my original expression. If you look back up to where I wrote PS, perfect square, that is represented in my original expression. So I can simply rewrite the standard form of my perfect square in factored form, which we found in this step, step 1, z minus 5 over 2 squared plus 7 over 4, which I got as the remainder from step 4. So, to summarize, I have my perfect square plus the remainder, which I calculated by rewriting my original expression to include the standard form of the perfect square I found in step 1. Let's try a second example. We have x squared minus 0.6x plus 1. Step 1 is to, again, focus on the a and b terms. What perfect square will factor to x squared minus 0.6x? I know that whatever the h value is, that is the number in my binomial, needs to be added twice to get negative 0.6. So that means my number will be half of negative 0.6, or negative 0.3. Notice that because of how we factor our expressions, this h term will always be exactly half of our b term when we're looking for the perfect square, because we'll end up multiplying negative 0.3 times x and negative 0.3 times our other x, then adding them together to combine like terms. That means we can always figure out our h value here by simply splitting our b value in half. Step 2 asks us to expand our perfect square. Of course, we end up with x squared minus 0.6x, and negative 0.3 times negative 0.3 gets us 0.09 as our c value. We can skip step 3 because the c term in our perfect square is not a fraction, and move on to step 4. We need to adjust our original expression, remember that's our example at the top, to include the c term from our perfect square. The c term from our perfect square, as listed in step 2, is 0.09. So just like the last example, I'm going to split up the c term in my original expression to include the c term from my perfect square. Notice that my two constants in step 4 are equal to 1. This expression is the exact same thing as this expression here. We simply wrote 1 as 0.09 plus 0.91. And I knew that these were the two numbers I wanted to add because the c term in my perfect square here in step 2 was 0.09. At this point, I'm ready for step 5. I can convert my perfect square to factored form. So notice that I have my perfect square, x squared minus 5x plus 0.09, just like it appears in step 2, and I can rewrite it in factored form, which I know from step 1 was simply x minus 0.3 times itself, or x minus 0.3 squared, and I have this leftover 0.91 that I'll be sure to include in my expression. All right, so here's where things get a little bit more tricky. Our next example is 2x squared plus 16x plus 3. Notice that the coefficient on our x squared value is no longer 1. We have 2x squared. Our first step changes. We need to group our x terms and factor out the leading coefficient. The leading coefficient meaning our 2, or the coefficient on our x squared value. If I factor out the leading coefficient of 2, grouping only the x terms, it looks something like this. 2 times x squared plus 8x. Notice that I've separated that from my 3. The 2 is being multiplied by the sum of x squared and 8x, not multiplied by my 3. So my 3 does not change. If I were to redistribute my 2, I would end up back at 2x squared plus 16x. 2 times 8 is, of course, 16. Now the next step is going to seem familiar. With the values I have in pink, that is, the x terms, I'm going to look for a perfect square. I can focus on what I have in parentheses because I've factored 2 out. So if I think about x squared plus 8x, what would a perfect square look like? Well, I know that my h term needs to add twice to get a positive 8. Of course, half of positive 8 is 4. So my perfect square will look something like this. X times x is x squared. Then we have 4x plus 4x. And then we've got 4 times 4, which is, of course, 16. And I can expand my perfect square, which is step 3. To summarize, I took my x terms and I looked for a perfect square, which would be the factored form here, x plus 4 times x plus 4. I knew that my perfect square that would achieve x squared plus 8x was x plus 4, because 4 plus 4 is 8. Step 3 asks us to expand our perfect square, and we're almost finished. I factored x plus 4 times x plus 4. I'm just going to redistribute my 2 for 2x squared plus 16x plus 32. I multiplied each term by 2. Now, step 4 should also be familiar. I'm going to adjust my original expression to include the c term from my perfect square. Let's take a look. The c term in my original expression is 3. The c term in my perfect square is 32. I need my original expression to include the number 32 so that I can include my perfect square. You might remember from Monday that when the c term in our original expression is less than the c term in our perfect square, we can go ahead and add the value we need to get to the c term in our perfect square. Again, this is our perfect square. The c term is 32. But however much we add, we also need to subtract, because we don't want to change the value of the expression. If I add 29 and subtract 29, I'm really adding 0, because 29 minus 29 is 0. At this point, I now have the entire perfect square as a part of my original expression. Remember that what I have written in step 4 here is exactly the same as what I have written here, because all I've done is add a kind of tricky 0, you could call it, 29 minus 29. Step 5 asks us to convert our perfect square to factored form. If we look here, we've got our perfect square in standard form, just like we did here in step 3. So I can go ahead and convert that part of the expression into factored form. I just put a purple line to identify the part of my original expression that includes the perfect square. It's exactly the same as the standard form of our perfect square that we found in step 3, which we found by expanding our perfect square in step 2. So we have a final answer of 2 times x plus 4 squared minus 29. It's okay if that felt a little tricky. Let's try another example. We have 3x squared plus 12x minus 8. Our first step is to group the x terms and factor out the leading coefficient. So I'll group 3x squared plus 12x and factor out the leading coefficient, which would be that positive 3. Looks like this. I end up with 4x because 3 times 4 is 12, and I factored out the 3. So we need to ask ourselves, what perfect square will factor to this a term and b term, meaning the a term and b term we have in our parentheses? I know that 2 plus 2 is 4, which means my h value will be positive 2. It looks like this, because when I factor out my expression, I'll end up with x times x squared, plus 2x times 2x, 4x, and a constant of positive 4, because 2 times 2 is 4. So I just got started on step 3, which is to expand that perfect square. I need to redistribute the 3 that I have outside my parentheses, and I end up with 3x squared plus 12x plus 12. Notice that the a value and the b value in my perfect square match the a value and the b value in my original expression. All that I've done is discover the perfect square, that is the binomial that can be multiplied by itself, that has the same a and b value as my original expression. In step 4, I'll return to my original expression here, and I need to think about how I can change this expression to include the c term from my perfect square. The c term for my perfect square is, of course, positive 12. Now, just like you saw in the last example, I need to change negative 8 to positive 12 without changing the value of the expression. So, to change negative 8 to positive 12, I need to add 20. But to maintain the same value of my expression, I need to subtract 20. Notice that if I add 20 and subtract 20, I've essentially just added 0. However, this will allow me to rewrite the expression as 3x squared plus 12x plus 12 minus 20. This step here represents the exact same expression as our original expression. This is equal to this. However, by adding 20 and subtracting 20, I'm able to rewrite it in a way that includes the standard form of my perfect square, which is, of course, what I discovered in steps 1, 2, and 3. But remember, this expression, and this expression are all the same, simply written differently. In step 5, I can finish up by converting my perfect square to factored form. I got my perfect square here, 3x squared plus 12x plus 12, and I'll rewrite it as 3 times x plus 2 squared, and I can't forget that minus 20 constant, which I included here. Notice my perfect square, underlined in purple, exists in my original expression when I rewrote it creatively in step 4. It's exactly the same as the standard form of my perfect square I discovered in step 3, and I got that from step 2, where I had the factored form of my perfect square. Notice that the factored form of my perfect square is exactly the same as the first term in my final answer. The only difference is that I wrote x plus 2 times x plus 2 as x plus 2 squared, because I'm multiplying what's inside the parentheses by itself one time. And that's your final answer. Why don't you give this one a shot and see how it goes? If you followed the steps correctly, you would have grouped the x terms, in this case they're p terms, and factored out the leading coefficient of 4. You have 4 times p squared minus 3p plus 13. Step 2 asks us to find the perfect square that factors to this a term and b term. We know that half of negative 3 is negative 3 over 2, or negative 1.5, however you wrote it. Step 3, we would expand our perfect square, which would give us 4 times p squared minus 3p plus 9 over 4. Notice that I have negative 3p as my b term because I end up with negative 3 over 2 times p, negative 3 over 2 times p. When I add those like terms together, I would end up with 6 over 2, which is simply 3, or in this case, negative 3. And my c term in my perfect square is 9 over 4 because I multiplied 3 over 2 times 3 over 2 for positive 9 over 4. So at this point, I simply need to redistribute my 4, which gives me 4p squared minus 12p plus 9. Again, notice that the a term and the b term in my perfect square are exactly the same as in the original expression. The only difference is this c term. I have positive 13 in my original expression, and I have positive 9 in my perfect square. So this is one of those ones that's a little bit easier because we can easily follow step 4, adjust our original expression to include the c term from our perfect square. I can rewrite 4p squared minus 12p plus 13 as 4p squared minus 12p plus 9 plus 4. Notice that 9 plus 4 equals 13, so this expression, and this expression are all exactly the same. 9 plus 4 is exactly the same as 13. Simply gotten a little creative. However, now I have my standard form of my perfect square, 4p squared minus 12p plus 9, included in my original expression. So I can convert that perfect square to factored form. Notice again that all I did to my original expression, which is here in black, was change my constant 13 to 9 plus 4, then convert the standard form of my perfect square, which I calculated in step 3, to the factored form. Just like our last example, the factored form I have in step 2 is exactly the same as my expression. I simply rewrote it as p minus 3 over 2 squared since I'm multiplying p minus 3 over 2 times itself. We'll stop here for today. If you're feeling challenged by finding the perfect square, especially with these a coefficients of not 1, please reach out to me for some extra help for an additional assignment. I want to make sure we're good on this before we move on to the next topic. Have a great rest of your week, guys.